Dear friends, I am Professor DGT going to take your lecture related with the CMOS logic family. Paper PPH 1802, lecture number 11. We have studied here two types of the logic family, TTL logic family, and then after we have studied about the CMOS logic family. Both the logic family, characteristics, etc. we have studied. And mainly, we have seen that what is their profile, what is their fan-out capability, what is the floating input, and how they are going to be compatible among the family only that we have studied. Now we are going to learn about TTL to CMOS interface and CMOS to TTL interface here. What does it mean? If one of this logic family gate, maybe the TTL, is connected as a TTL driver and output of the TTL driver is connected to the CMOS input. CMOS IC input we are going to connect. Both the logic family has supply voltage is a different range. TTL can work only on the 5 volt regulated power supply. Plus minus 0.25 volt is allowable, and commercially 0 to 70 degrees Celsius is the temperature range for the TTL is there. For the CMOS, that temperature range is from minus 40 degrees Celsius to plus 85 degrees Celsius. But the great advantage is its voltage variation. The CMOS can operate at the supply range of 3 volt to 15 volt. That means it is having a flexible supply voltage. So, output of the TTL gate, if we connect to the input of the CMOS interface, then how and what various way we can make this interface, that we have to study here. And there are different methods for that, and that different method we are going to learn over here. The word interface, so we are starting with this one, 14.11, TTL to CMOS interface. The word interface refers to the way a driving device is connected to the loading device. In this section, we discuss the method of interfacing CMOS devices to the TTL devices. Recall that TTL devices need a supply voltage of 5 volt while CMOS devices can use any supply voltage from 3 volt to 15 volt. Because the supply requirement differ, several interfacing schemes may be used. Here are a few of the more popular methods we are going to discuss. So, the first we are going to study about the TTL to CMOS interface. That means TTL will be working as a driver. So, output of the TTL is connected to the input of a CMOS devices. So, we have to see the output profile of the TTL and input profile of the CMOS. Are they compatible for the low state as well as for the high state or not? And if it is not, how we can make them compatible, what we can do for that, that we have to learn over here. So, for the TTL, there is no option. It can work only on the 5 volt. CMOS can work from 3 volt to 15 volt. So, there is one possibility that both can operate at the 5 volt. TTL is also operating with the voltage 5 volt as well as CMOS also can operate at the 5 volt. Then is there compatibility is not there or not? The first thing we are going to learn about that things. So the first case is supply voltage at the 5 volt. What is going to be happen? One approach to the TTL to CMOS interface is to use a 5 volt as a supply voltage for both TTL driver as well as the CMOS load. In this case, the worst case TTL output voltage, figure 14.38a, are almost compatible with the worst case CMOS input voltage, figure 14.38b. List 14.38a are TTL output characteristics and with the window, and figure 14.38b is input characteristics of the CMOS when it is operating at 5 volt. So from the first sight, it looks that they are going to be compatible. But deeperly, if you study that, they are almost compatible, but not quite. And that we have to see here. TTL output window, when it is going to be in a worst case conditions, it can be a maximum voltage of 0.4 volt. So it is from 0 to 0.4 volt. So VOL maximum is going to be 0.4 volt. And CMOS input, when the input is going to be low, that is can accept up to 0 to 1.5 volt. So 0 to 0.4 volt window, output window of the TTL can fit inside the input window low state to the CMOS devices. So for the low state, they are completely compatible and there is no problem. But what about the high state windows? TTL output in the high state, ideally it should be 5 volt, but in the worst case, it can be lower up to 2.4 volt. But in a CMOS input, is valid high state input can be from 3.5 volt to 5 volt. That means minimum it requires 3.5 volt. So if the TTL in the worst case less than 3.5 volt, it can be up to 2.4 volt. Then also it is valid high state output is there. But if that is connected to the CMOS input, then CMOS cannot consider as a valid high state input. And in that case, it comes to the indeterminate state, or output can be of the CMOS will be high or low. It doesn't recognize this input as a high or low. So it is indeterminate state is going to be there. There is no problem with the TTL low state window 0 to 0.4 volt because it fits inside the CMOS low state window 0 to 1.5 volt. The connection is like this. This is the TTL driver. Its VCC voltage is connected with the 5 volt and CMOS is also connected with the VCC voltage of 5 volt. So both are operating at the same 5 volt. Now output of the TTL is connected as an input of the CMOS. We can see here in this figure 14.39. So this is called TTL driver and CMOS load. This is the TTL output profile and this is the CMOS input profile. TTL output profile, when TTL output is going to be low, it can be in between 0 to 0.4 volt. And when the TTL output is going to be high, it can be 5 volt but it can be minimum up to 2.4 volt, then it is valid high state TTL output is there. And indeterminate window is 0.4 volt to 2.4 volt is there. In case of the CMOS input profile, the input window, low window is from 0 volt to 1.5 volt. So low window of 0 to 0.4 volt can fit inside 0 to 1.5 volt of CMOS low window. So input low state is compatible with the TTL. But in the high state, output window doesn't fit inside the high state output window of the CMOS and hence it comes to the indeterminate state. This means the CMOS load always interpret TTL low state drive as a low. The problem is in the TTL high state, which can be as low as 2.4 volt. See figure 14.38a. TTL output profile in a high window. If you try to using a TTL high state output as the input to the CMOS device, you get indeterminate action. The CMOS device need at least 3.5 volt for a high state input. So minimum voltage of the CMOS input in the high state is required 3.5 volt and above that. But if it is 2.4 volt and to 3.5 volt, of the TTL output, then it is indeterminate state. Because of this, you cannot get reliable operation by connecting a TTL output directly to the CMOS input. You have to do something extra to make the two different devices compatible. So directly it cannot work. So something has to be done so that two devices can be compatible to each other. What do you do? The standard solution is to use the pull-up resistance between the TTL driver and CMOS load, as shown in the figure 14.39. So we have seen that in this circuit, there is a between this TTL output and CMOS input. This resistance 3.3K is connected between the VCC and output of the TTL. So this resistance is known as a pull-up resistance. It will pull the output voltage up to the 5 volt when the output of the TTL is going to be in the high state. What effect the pull-up resistance have? It has almost no effect on the low state, but it does raise the high state to approximately plus 5 volt. For instance, when the TTL output is low, the lower end of the 3.3 kilo ohms is grounded. What is the output of the TTL? You visualize mentally that there is a 130 ohms resistance, then there is a transistor Q3, then there is a diode D1, and then there is a transistor Q4, which is a saturation transistor, and it is connected to the ground. Collector of the Q4 is taken as output. So when the output of the TTL is going to be low, the lower transistor Q4 is conducting, or it is in a saturation, so almost it is at a ground potential. That means lower leg of the 3.3 kilo ohms resistance is at the ground potential, and the current is passing through that resistance and passing through the, or it is sinking through the transistor Q4 to the ground. Now, how much current is passing through this one? That depends upon the voltage and value of the resistance. V upon R is the current. So the voltage is going to be 5 volt divided by 3.3 kilo ohms resistance. Approximately 1.52 milliampere current is sinking through the transistor Q4, which is having a current capacity IOL maximum is 16 milliampere. So that 1.52 milliampere current, when it is passing through the transistor, it makes no problem. So in a low state, it works very well. Therefore, the TTL driver sinks a current of roughly I is equal to voltage 5 volt upon 3.3 kilo ohms resistance, that is approximately 1.52 milliampere. When the TTL output is in the high state, the lower transistor is disconnected. The lower transistor Q4 is not conducting, it is off. That means it is open switch. Only the upper transistor Q3 is acting like emitter follower. And when the upper transistor is conducting, VCC is coming as output, and almost it is going to be between 2.4 volt to 3.9 volt. So in a worst case conditions, it can bring the output voltage of 2.4 volt, that is the lower leg of 3.3 kilo ohms resistance. But because there is no current is passing through this resistance, so what happens? The lower leg of the resistance is also at a 5 volt, as its upper leg of the resistance is at 5 volt. So it will pull up the voltage, output voltage of the transistor to the 5 volt. So when the TTL output is going to be in high state, it will raise the voltage from 2.4 volt to the 5 volt, and which is compatible for the CMOS input, which is supposed to be required greater than 3.5 volt. When the TTL output is in the high state, however, the output voltage is pulled up to the 5 volt. Here is how it happens. As before, the upper totem pole transistor actively pulls the output voltage up to plus 2.4 volt in a worst case conditions. Because of the pull-up resistance, however, the output rises about 2.4 volt, which forces the upper totem pole transistor into the cutoff. And because of that, the output voltage is going to be 5 volt. Even Q3 emitter follower becomes off, and both the transistor will be off. That means passive pull-up circuit is going to be there now. So any input capacitance of the CMOS, which is going to be charged through, or its voltage is going to be built up at the input of the CMOS through the resistance 3.3k ohms, and because the RC time constant is depending upon the value of this resistance. If the value of resistance is going to be higher like this 3.3 kilo ohms or something, the charging time will be taking more. That means input value is set up with a longer period of time, and hence you can say that the propagation delay time is going to be increase of the CMOS also, and hence what happens, the actions becomes slower or speed of operation is slower. The pull-up action is now passive because the supply voltage is pulling the output voltage up to the plus 5 volt through the pull-up resistor. The gate capacitance of the CMOS load has to be charged through the pull-up resistor. This slow down the switching action because RC time constant is going to be higher. In a normal TTL output resistance is only either 12 ohms or 70 ohms, but now it is going to be 3.3 kilo ohms through which that input capacitance is going to be charged, and hence RC time constant increases, which will slow down the action of the circuit. If the speed is important, you can decrease the value of the pull-up resistance. So to decrease this RC time constant, you cannot manipulate with the resistance capacitance, input capacitance, because it is a stray capacitance. You cannot change it, only you can change the value of the resistance, and to lower the RC time constant, you can reduce the value of resistance R from 3.3 kilo ohms. How much this value of the resistance R can be reduced? Who puts the limitation over this value of R? That is, when the output of the TTL is going to be low, then the lower transistor is conducting and the current is sinking through that transistor because the lower leg of the resistance is going to be at zero potential. The maximum current can sink through this transistor for a standard TTL is going to be 16 milliampere current. So 5 volt divided by the 16 milliampere current maximum, that is supposed to be the value of the resistance. That comes around 328 ohms or 330 ohms, which is typically near to 328 ohms available in the market. The minimum resistance is determined by the maximum sink current of the TTL device. TTL device output, when it is going to be low, can sink maximum current. IOL maximum is equal to 16 milliampere current for the standard TTL. In the worst case, the supply voltage may be as high as 5.25 volt because it can tolerate plus minus 0.25 volt. So in a worst case, it can be high as 5.25 volt. So the minimum resistance R is equal to 5.25 volt divided by the current. V upon I is nothing but the value of the resistance. So that comes out to be 328 ohms. The nearest standard value which is available in the market is 330 ohms, which you should consider the absolute minimum value for the pull-up resistance. So to speed up the actions, you can reduce this pull-up resistance minimum up to 330 ohms only. You cannot lower than that. And you would use this only if the switching speed were critical. And because the current draining is going to be very high, better not to utilize this lower value of the resistance. Only when speed of operation is critical, that is very important, then and then only you reduce the value of the resistance from 3.3 k ohms. Otherwise, that 3.3 k ohms is typical. In many applications, a pull-up resistance of 3.3 kilo ohms is fine. Incidentally, the other inputs of the TTL driver and CMOS load are connected to the signal lines. which are not shown over here. So here in a circuit there are 3 input TTL is there and 3 input CMOS is also there. We have not shown here that where these inputs are going to be connected, but they may be connected to the signal lines. And similarly for CMOS, other input is also connected to some signal lines, that means output of some gates. If more than one TTL chip is being interfaced to the CMOS load, connect each TTL driver to the separate pull-up resistor and CMOS input. Now, when the CMOS is operating at a 5 volt, then it is having a more propagation delay time, and its propagation delay time is going to be increased and its noise immunity is going to be decreased. So it will suffer the advantage of the CMOS. That means the propagation delay time is going to be propagation delay time is going to be increased and the speed of operation is going to be reduced. And because the voltage is going to be decreased, so noise immunity is also going to be decreased. Therefore, it is better to run CMOS devices with a supply voltage between 9 volt and 12 volt, 9 to 12 volt. So, that is the best compromise. We have studied actually in the CMOS characteristic that CMOS can operate between 9 to 12 volt, then it is the best compromise for the speed of operation, noise immunity and overall performance. So one way to use the higher supply voltage is with the open collector TTL. How we can do this thing then? There are two things. TTL can only operate at 5 volt and CMOS can have any voltage between 3 volt to 15 volt, but it is best way to utilize between 9 to 12 volt. So one way to operate TTL other than 5 volt is to utilize as an open collector TTL circuits, where collector of the TTL is going to be open. That means saturation transistor output totem pole arrangement will not be there. TTL is operating at 5 volt VCC, but its output collector is floating. It is not connected anywhere and it can be connected through a pull-up resistance to any supply voltage. It can be connected with the supply voltage of the CMOS also. Then output in a low state it can be 0 and in high state that output will be actually the supply voltage of the CMOS, and that way the CMOS can operate with a higher supply voltage. So we can now study about the different supply voltage. CMOS performs deteriorates at lower voltage because the propagation delay time increases and the noise immunity decreases. Therefore, it is better to run CMOS devices with a supply voltage between 9 and 12 volt. One way to use the higher supply voltage is with the open collector TTL driver, figure 14.40. Recall that the output stage of the open collector TTL device consists only of a sink transistor Q4 with a floating collector in figure 14.40. This is just a circuit diagram. Open collector TTL devices. TTL is running with the 5 volt VCC. Ground and VCC is connected. Output of the TTL, instead of totem pole arrangement, there is only one transistor Q4 is there, saturation transistor, and its collector is floating. So normally it cannot work without pull-up resistance. So that is output of the collector of the TTL is connected through a pull-up resistance 6.8 kilo ohms to the supply voltage of 12 volt. So now when the output of the TTL is going to be low, it will be between 0 to 0.4 volt, and when the output of the TTL is going to be high, because no current is passing through the sink transistor, the output voltage will be approximately 12 volt, which is the input for the CMOS device, and CMOS device can work with the supply voltage of 12 volt. So properly compatible like this way. So both can operate with a different voltage. TTL can operate with the plus 5 volt and CMOS can operate with the plus 12 volt. This open collector is connected to supply voltage of plus 12 volt through a pull-up resistance of 6.8 kilo ohms. Likewise, CMOS device now has a supply voltage of plus 12 volt. So CMOS device can operate at higher voltage plus 12 volt or any other voltage. When the TTL output is low, we can visualize a ground on the lower end of the pull-up resistor. Therefore, TTL device has a sinking current is equal to, because voltage is going to be 12 volt and the value of the pull-up resistance is 6.8 kilo ohms. So, the current which is going to be passing through the sink transistor Q4 is 1.76 milliampere current when the output of the TTL is going to be in the low state. When the TTL output is in the high state, the open collector output rises passively to the plus 12 volt because the sinking transistor is cut off. So it is not working. And because the TTL output is floating, the output voltage is nothing but the lower end of the resistance, pull-up resistance, and that will pull up to the 12 volt. In either case, the TTL output are compatible with the CMOS input state. So this way, both can operate with a different supply voltage. The passive pull-up in figure 14.40 produce slower switching action than before. Whatever we have discussed earlier, same thing can be applied here, because now the output transistor is not conducting. That means now it is a passive pull-up is there, because output voltage when it is going to be in high state, it is going to be 12 volt. And that 12 volt is the input to the CMOS. So this 12 volt is actually rising across the input capacitance of the CMOS. That input stray capacitance, maybe you can consider it may be 10 pf or something. That means RC time constant is required to charge that 10 pf capacitance from 0 volt to 12 volt. And for that, the RC time constant is nothing but 6.8 kilo ohms multiplied by 10 pf, approximately 68 nanoseconds is required to change the input voltage of the CMOS from 0 volt to 12 volt. So it will set up the 12 volt or high state after the 68 nanoseconds. The passive pull-up in figure 14.40 produce a slower switching action than before. For instance, with a gate input capacitance of 10 pf, the pull-up time constant is RC is equal to 6.8 kilo ohms into 10 pf, that is approximately 68 nanoseconds. So even the input changes from 0 to 1. For the CMOS, it takes 68 nanoseconds, and thereafter it will reflect to the CMOS output. So overall propagation time is going to be rising very large, or the speed of operation is going to be decreased. If this is a problem, reduce the size of the pull-up resistance to its minimum allowable value of this pull-up resistance. How we can decide that what should be the minimum value of the pull-up resistance? Because the current capacity of the open collector TTL output, if it is standard, then it can pass a 16 milliampere current when the output is in low. So 12 volt divided by 16 milliampere current, that give you the value of the resistance is approximately 750 ohms will be there. That means you can reduce this size of the pull-up resistance all the way from 6.8 kilo ohms to 750 ohms minimum in between any value, so that RC time constant can be reduced and the speed of operation can be increased. The pull-up time constant decreases RC 750 ohms into 10 pf, approximately 7.5 nanoseconds. That means we can reduce from 68 nanoseconds to 7.5 nanoseconds if this pull-up resistance becomes minimum, that is of 750 ohms allowable. So this way we can, another way we can make interface between the TTL and CMOS. There is a third method is also there, and that third method is we are utilizing CMOS level shifter. So there is a CMOS IC available, and that IC is 40109, which is called a level shifter. It will shift the level from output of the TTL which may be from 2.4 volt to 5 volt. It can be shifted to the required level for the CMOS. That is, CMOS may be working 12 volt, it may require 12 volt, so that is going to be possible using this CMOS level shifter IC. So this CMOS level shifter IC requires two power supply. Input side it is working with the 5 volt supply, and output side it is working with the 12 volt supply. Figure 14.41 shows a 40109 called a level shifter. The input stage of the chip uses a supply voltage of plus 5 volt for compatible with the TTL, while the output stage uses plus 12 volt compatible with the CMOS devices. So in other words, the input stage interface with the TTL and output stage interface with the CMOS. You can see this circuit diagram. This is the TTL. It is working with the 5 volt and it is open collector TTL, remember. So here there is a pull-up resistance is there of 3.3 kilo ohms. This is the IC 40109 CMOS IC is there, which is nothing but working as a level shifter. Input side of this IC is operating with the 5 volt and output side of this IC is operating with the 12 volt. CMOS is also operating with the VCC of 12 volt, remember. So what happens now? CMOS level shifter allows the use of 5 volt and 12 volt supply. In figure 14.41, a standard TTL device drives the level shifter. This produces action active TTL pull-up to at least plus 2.4 volt. Beyond this level, the pull-up resistance takes over and raises the voltage up to 5 volt, which ensures a valid high state input to the level shifter. The output side of the level shifter connects to the 12 volt. This can be changed to any voltage from 3 to 15 volt. You can see that how it will work. When the TTL output is low, that means the output voltage can be any voltage from 0 to 0.4 volt. This is CMOS IC. So 0 to 1.5 volt is allowable, no problem to it in the low state. In the high state, this TTL output can be in the worst case conditions. It can be minimum up to 2.4 volt, and from 2.4 volt, because of this pull up resistance, it can be pull up this voltage up to the 5 volt through this pull up resistance 3.3 kilo ohms, which is more than 1.5 volt for the CMOS input, and more than 1.5 volt it will more than 3.5 volt it will consider as a valid high state input, and that way the compatible to the CMOS input. But output of this CMOS level shifter, it is shifting from 5 volt to the output of this one is going to be 12 volt, which is considered as a very valid high state input for the CMOS load. This produces active TTL pull up to at least plus 2.4 volt. Beyond this level, the pull up resistance takes over and raises the voltage up to plus 5 volt, which ensures a valid high state input to the level shifter. The output side of the level shifter connects to the plus 12 volt. This can be changed to any voltage from 3 volt to 15 volt because it is CMOS level shifter. Since the CMOS load runs off of 12 volt, it has a better propagation delay time and noise immunity. That means propagation time is not going to be suffer, and its noise immunity is also not going to be decreased. In summary, a TTL has to run off of plus 5 volt, but CMOS does better with a supply voltage of plus 12 volt. This is the reason for using a level shifter between the TTL driver and CMOS load. Thank you, dear friends.